One important question is, what does the Bible say about creation? And I'm sure you've seen this picture from the James Webb Space Telescope, just an amazing view into space. And what does the Bible say about the flood? Here is, I'm sure you've all seen this chart, the biblical genealogies in Genesis 5 and 11 from Adam to Abraham. And something that's interesting is that the genealogies, they're found in Genesis 5 and 11, of course, but they're also found in 1 Chronicles 1. And in 1 Chronicles, the author includes the names of multiple sons of each patriarch. And that's actually really helpful for genetic studies and for understanding history. And then Matthew, of course, includes Jesus's genealogy back to Abraham, and Luke, who was writing to the Gentiles, includes Jesus's genealogy back to Adam, which that makes sense because the Gentiles wouldn't have necessarily known by heart the genealogy from Abraham to Adam. Mentions of Adam in the Old Testament and the New. And Moses said that God separated the sons of Adam. Job referred to Adam covering his transgressions with fig leaves. Romans, Paul, Corinthians, Timothy, Paul talks about Adam a lot. He said that Adam was the first man. He said that Adam was formed first and then Eve. And Jude, probably Jesus's brother, mentions that Adam was the seventh. Enoch was the seventh from Adam. Mentions of Noah, Isaiah. In Isaiah, God said, "I've sworn that the waters of Noah should no more go over the earth." In Ezekiel, Ezekiel mentions Noah, Daniel, and Job. Matthew talks about the days of Noah. Luke talks about the flood and Noah entering the ark. In Hebrews, Paul talks about Noah and the flood in the ark as well. Peter talks about Noah, the flood, and the ark. And okay, so a big question is how to read the Bible. What is the correct hermeneutic? And helpful questions to answer that question are, well, what did the author intend to convey? In what context was the author writing? What was going on? How does the author's writing address what was going on? And how should this inform and instruct us right now? Like, how should we, in what way is this, like, what are we supposed to do with what the author's intent was? So obvious question, I think, is how did Jesus read the Old Testament? How did the writer of Chronicles view the genealogies? How did Luke view them? And the answer, of course, is that they viewed them as part of their personal history, the history of their nation. There's no indication that they thought that this was metaphorical in any way. It was all just, these were real people who were their ancestors. And many people claim that this is not a sophisticated way to read the Bible, but are we trying to be sophisticated, or are we trying to be like Jesus? What are the consequences of giving up a straightforward reading of the text? And we'll talk about, that's something to think about, and we'll talk about it more later. For now, what's the point of giving up the most straightforward reading of the text? So I was in a Bible study, a Sabbath school class here at church, and it was the presenter, the main leader of the Sabbath school class was an eminent physician, world famous, brilliant man, and he expended a lot of energy trying to convince people that the biblical chronology was not correct and the evolutionary chronology was correct. And so one time in class, someone asked him, do you understand what you're giving up? Do you realize what you're giving up? And very quickly he said, yes, but if we don't accept the evolutionary timescale, we won't have a seat at the table of scientific discussions. So you can see where his priorities were. The text that jumped into my mind right then was, from James chapter 4, ye adulterers and adulteresses, know ye not that friendship with the world is enmity with God? And I would add that in order to really be accepted at that table, the table of secular scientific discussion, we have to agree, or at least speak and act as though the universe created itself. God had nothing to do with it. Life just happened as a result of chemical processes. God did not design it. All life on Earth evolved from the first living cell, and God was not involved. And these processes happened over billions of years. So just to clarify, one doesn't have to claim to be an atheist to be given a seat at the table of scientific discussion, but one does have to speak and present their research as though God never does anything. So it's invoking God's intervention in the universe that is taboo. Okay, where do the scientific data actually point, though? Here's a few answers in a nutshell. Did the universe create itself? Well, no. The universe is carefully designed for life. God balanced everything necessary for our survival on an absolute knife edge so that science would unmistakably point straight back to him. And what's fascinating is that it doesn't matter what view of the universe you take. This is true even if you accept the Big Bang model. I was watching a really short video. Somebody had filmed it in the car, and this was a friend of Christopher Hitchens, and they were in the car. He asked Christopher Hitchens, is there anything that gives you pause? Is there anything that makes you wonder about this? And he was speaking about his atheism specifically. And Christopher Hitchens' reply was the fine-tuning of the universe. Like, he knew that the universe really looked like it was designed for life, and for us specifically. Okay, so did life come about by chance? I would say no. The laws of chemistry are absolutely contrary to the generation of living cells from minerals. God carefully engineered life so that it could protect itself from normal chemical processes. So just to give you a quick example of how this works, your DNA in every one of your cells, your DNA suffers about 10,000 lesions per day just from intrinsic damage created by just normal chemical processes. And you have many, many little repair mechanisms, little machines, little molecular machines that run around inside your cell, and they fix your DNA. And if you didn't have these little machines, all of our DNA would fall apart pretty quickly, and we'd die very, very fast. And so which came first, the DNA or the little machines that fix the DNA? That's not a trivial question. It's one of those things where you look at it and it's very carefully engineered so that it can just continue living. And so the reason I bring that up in the question of did life come about from minerals is that a lot of people will say, oh, well, life came about first. There was RNA and then there was DNA. Well, RNA is more fragile than DNA because there's only one strand. The two strands of the DNA actually help each other out. They're more resistant to being pulled apart by chemical processes. The one strand of that RNA, it's very fragile. They have to keep that vaccine at like negative 70 degrees Celsius or something just to keep it from falling apart. It's extremely fragile, and we want it. It needs to be fragile. God designed it to be fragile because you don't want that RNA creating a bunch of protein inside your cell that you don't need, because that's its job. And so it's all just carefully designed. Every bit of it is just very, very carefully designed. Okay, did all life evolve from a single cell? No, genetic mutations degrade genetic information. Genetic mutations, they won't make us superheroes. They give us metabolic problems. They create other problems. And we know this. This is pretty obvious science. Natural selection destroys genetic information by killing individuals that are not fit for the environment. So that's just not a good way to encourage diversity of genetic information. So both of these processes are pushing life downhill, not up. Okay, have billions of years passed since the creation of the Earth? Well, that's what I wrote this book about. This is my specialty, and I'll be talking more about just the geology, answering that last question. So my goal is to contribute to a new scientific model and not just tear down the secular model. I think that's more fun, it's more rewarding, and I think it's just better for science. Um, and to explain what a model is in science, imagine I just hand you one of these puzzle pieces and say, can you please describe to me what this is? Like, what is this depicting? And it's going to be difficult just looking at one piece. You need a model to help you put that piece into place and understand it in a bigger context. And so once you have the box of the puzzle, now you can see, well, that piece on the left is probably the edge of a bubble. The piece on the right is probably part of a box with some French writing on it. It's a lot easier to put your scientific data into perspective if you have a model to do that with. And so that's the purpose of scientific models. We have a saying that says all models, we have some models are helpful and no models are true. And if scientists remembered that, it would help a lot. Okay, so this book here, I've gone over 9 independent arguments for a young Earth. And the word independent here is important because it's 9 completely separate arguments that all point the same direction. And a scientific case is a lot stronger the more arguments point in that direction. And I wanted each of these arguments to be accessible and verifiable to people who are not geologists. So the one we're going to talk about right now is coastal erosion. And if you go to Google, you can plug in what is the erosion rate of the California coast, and it'll tell you it's between 0 and 42 centimeters per year. And then you can say, well, what's the erosion rate of the East Coast? And then say it's about 80 centimeters, about 0.8 meters or 80 centimeters per year. And you say, how wide is the United States? It's about 4,200 kilometers, depending on where you measure. Well, 4,200 kilometers is 420 million centimeters. Now that's a lot of centimeters, but we're losing 100-ish every year. Well, if you divide 420 million by 100, that means that the erosion of the coasts would destroy the United States in 4.2 million years. Well, 4.2 million years sounds like a lot, but it's just a tiny drop in the bucket of deep time. Like if you think about the dinosaurs are supposed to have lived 60, 100 million years ago. Life, the earliest complex life is supposed to have, evolved a few 100 million years ago. But in just 4.2 million years, the coasts would destroy the entire continent. And you can see this process happening when you go to the ocean. This, of course, this cliff didn't used to be here. The ocean eroded that away and caused this cliff. These cliffs didn't used to be here. That land used to extend far out to the right, and it was chewed away and ended up on the deep sea floor as a result of coastal erosion. And sometimes it affects people. Often it affects people. This is a hurricane in Florida, and you can see that it's taken out the ground underneath that house. Same hurricane took out the ground from underneath another house, and it reminds me of Jesus's parable about building houses on sand. Coastal erosion consumes over $500 million in property each year in the U.S. So it's a significant problem. Lighthouses showcase this problem in an interesting way. So lighthouses, they're of course they're built on the coast, and this particular lighthouse was built in Rhode Island. They're usually built a few hundred feet back because they know about coastal erosion. But the problem is that if your erosion rate is a few hundred feet every century, then your lighthouse will be in danger after 100 years. And that's exactly what's happened all up the East Coast. So with the erosion rate of a little over 2 feet per year in Rhode Island, they had to move this one back to save it. Again, 2 feet per year. In Massachusetts, they had to move this one back to save it. And someone might say, oh, maybe the continent was really big in the past and what we have left is just a remnant. But you can see the entire continent here in the map. It's the light area that stretches out into the ocean a little ways beyond the land. And it's just not that big. It's consistent with a few thousand years of erosion. The continental crust is a lot thicker and it's not as dense as the oceanic crust. The oceanic crust is much thinner and it's quite dense. And so that's why the continent is floating so high above the ocean. Okay, so there's another form of erosion, though, that is destroying the continents, and we'll call it basinal erosion. That's how fast the basins are eroded out and carried down the rivers to the ocean. And in order to sort this one out, we need to ask how much land is on Earth, and it's about 150 million square kilometers. What is the average elevation of the continents? It's about 0.835 kilometers. And so if we multiply those two values, we get 130-ish million cubic kilometers of land on the entire Earth. Well, how much sediment does the Amazon River carry? It's about 1/3 of a cubic kilometer per year. So you can see that just the Amazon could destroy all of the land on Earth. I mean, if it had access to it, it could destroy all the land on Earth in a pretty short period of time, geologically speaking, from secular worldview. How much sediment do all the world's rivers transport annually? It's about 5.6 cubic kilometers if you ask Google. And when I say if you ask Google actually will pull up scientific papers. If you ask these questions, it'll give you options of scientific papers to look at. Another thing we need to know is what is the density of the Earth's crust? And it's about 2.7 grams per cubic centimeter, and which is about 2.7 metric tons per meter cubed. So if you do the math, you run all the math through, what you end up with is all the land on Earth could wash out to sea in 22 million years. Now, this is not even including coastal erosion. Now, 22 million years, again, it sounds like a lot, but it's just a drop in the bucket of what's supposed to be deep time, the 3.5 billion years of Earth's history. So now something else I want to point out here is that 22 million years is probably too long, because it's actually a little bit difficult to measure how much sediment a river carries. Now, you can dip a cup into the water and you can measure the sediment in that cup of water, but the river actually pushes a lot of sediment along on the bottom, and that part is difficult to measure. And I think that they've really underestimated that problem. And the reason I think that is, well, I mean, several reasons. From my own research, I think that, but also if you ask engineers how much sediment collects behind dams, dams lose about 1% of their capacity every year to sediment buildup. And that comes out to about 50 cubic kilometers per year in all the world's existing dams. Well, if you divide the volume of all of Earth's land by 50, you only end up with about 2.5 million years. The number is about 2.5 million. So that means that in 2.5 million years, you could collect all of the world's land behind the existing dams if such a thing were physically possible. So again, that's kind of wild that there's that much sediment washing into the dams every year. And engineers aren't making this up. These are numbers that they actually have to deal with regularly. So here's some erosion. This happens all the time, and I'm sure you've all seen local floods that have washed quite a bit of material out. This one, I included this one because the structures look a lot like Bryce Canyon. Just thought that was interesting. So if you look here and then back to this one, it's a little mini Bryce Canyon. You can see the grass up on the side of the wash there. Now, what's interesting about Bryce Canyon is that it's still being eroded. So if we look at the tree that's off to the right of that image, I'll zoom in a bit. And you can see that the tree started growing when the ground was up quite a bit higher. And the ground got eroded out, and now the roots are just all sticking down into the earth there. So just in the lifespan of that one tree, you can see how much the edge of Bryce Canyon has been eroded. And again, it's like, the earth is huge, right? There's an awful lot of land on earth. But when you multiply just that much erosion by millions and even billions of years, it starts to become extremely, these minute effects can have huge consequences over that much time. So the economic impact of soil erosion in the United States costs the nation about $37.6 billion each year in productivity losses, and damage from soil erosion worldwide is estimated to be about $400 billion per year. So again, soil erosion, this is something that people have to deal with pretty regularly. So they're not just making up random numbers here. Something else I want to talk about is bioturbation. So bioturbation happens when organisms that live or burrow into the earth, they churn up the sediments. So crabs, ants do this a lot, moles, earthworms, gophers. These guys will dig through the topsoil and they'll turn it over. And this is actually important for the plants. It's good to have the soil turned over regularly. And it's not just animals. The roots also do the same thing. Well, so about geology, what's interesting though is that if you go out and look at most of Earth's geology, you don't really find bioturbation. You don't find burrows. Now, I have a picture of some burrows here. I hope you can see it. There's a kind of some white stripes in the rock, and they get disrupted. And what's disrupting them is actually a burrow of a shallow marine organism. So sometimes you do find burrows. But often, this is a burrow. This one has been excavated, so I'm holding it upside down. But this is this is a cool burrow. Some of them form these nice shapes. Most of them are not this organized. So this is an example of hummocky cross stratification. It's just the type of structure that you're seeing there in the rock. And notice that there just aren't really burrows going through it. This is a shallow marine environment, and so you would expect a lot of burrowing organisms, but there aren't any. There weren't any. I shouldn't say there weren't any. They did live here, but they didn't have time to burrow during the deposition of this material. This is Anza Borrego here in California, and again, you can see that there just aren't many burrows going through this. There aren't any burrows here. I think I took this picture in Utah, and it's just one layer on top of another, and there aren't any burrows in there at all. So what that means is that these layers came down pretty quickly, because it's not that there weren't organisms to burrow. It's just that, again, they just didn't have time to burrow. And we can see that because sometimes we do find the burrows in a layer here or there. Like they had just enough time to like squiggle across the surface sometimes, and then more sediment came down. These are some beautiful layers. This is Arizona. This is the Chinle Formation. And you can see how nice these layers are. There's a close-up of it. Now, if the burrowing organisms had dug through it, it would have mixed all of those colors, and we wouldn't have this, like, it wouldn't look interesting at all, really, I don't think. But because it didn't get mixed, we have these nice layers. This is sandstone. This is the Navajo Sandstone. And again, you can just see that there's no bioturbation in there at all. It just left these beautiful lamina behind. So I wanted to talk a bit about my research in the Pisco Formation. The Pisco Formation is down in Peru, and it's an amazing area for looking for fossils. I've seen whale fossils. I did my research on whale fossils, and a dolphin fossil, but we also saw penguins, cormorants, seals, lots and lots of fish. I found a fish vertebra the size of a small dinner plate. Megalodon, the huge shark, we found plenty of megalodon teeth and other shark teeth, stingray teeth, huge stingray teeth. And there was a whale there that's called the Leviathan, and they think that it ate other whales. So it was a pretty interesting ocean. There's even some giant sloth skeletons in the Pisco Formation because sloths take to the water at times. So Wikipedia will tell you that the Pisco Formation is 640 meters thick, and it was deposited over 13 million years. Well, if you do the math, that comes out to 1 centimeter every 200 years, or 1 inch every 500 years. So 1/500th of an inch every year. And if you do the math again, you realize that's 1 grain of sand thick every 10 years. Just a grain every 10 years. Well, this is a shallow marine environment with a lot of sediment coming in from the coast. That just doesn't make sense at all. Anyway, we'll keep going. You'll see other reasons. So here's the location. It's down in kind of southern Peru, just north of the Nazca lines. If you've seen pictures of those or gone down to visit them. And this is what the area looks like. It's desert. It never rains out there, like almost literally never rains. And that's great for geology. You can see that there are not any plants to speak of. There is one plant that lives out here. It's this beautiful flowering, has this nice red flower, but the plant doesn't even have roots. It just sits on top of the soil and just kind of absorbs dust and moisture from the air. Or I'm sure it gets its minerals from the dust. So anyway, this is that area. And because it doesn't ever rain, well, I don't know, it was super windy some days, and the sand and dust would blow into our eyes, and so we taped our glasses to our faces. Kept working. Here we are cleaning off a whale, and the bed that I'm standing on is a layer of volcanic ash, and you can't see it very well, but I drew a picture so you can see what's going on. So there's sediment, there's a whale, there's water. The whale died, it landed on the bottom. Just some sediment collected around it. The volcanic ash layer collected, like it fell on the whale's back and slipped down the sides. More sediment collected, and then the whole thing was compacted and the whale decayed. So notice here that all of these layers were deposited before the whale decayed. So that's several feet of sediment that was deposited in just a few weeks. There's no 1 grain every 10 years going on here. Here's another whale, and if I step back, well, you can see the kind of the head of the whale, the skull off to the right. You can see some ribs to the left, not far left, but kind of middle left. And then you can see the bone that's closest to the camera is one of the right, it's from the right flipper. And if I step back, you can see some scours, some deep scours in the seafloor. And they're filled with a white material. That white material is volcanic ash. And that hummocky cross stratification that I mentioned before, it's all through here, all through the whole Pisco Formation. And that typically forms in hurricane-like conditions. So these were very tumultuous conditions. And there was a lot of volcanic ash falling out of the sky. There was a lot of sediment coming in from the coast. And these things are getting buried very quickly. And another way we can tell that they were getting buried very quickly we found baleen. And the baleen actually has protein in it, which is interesting. We wouldn't expect protein to last for millions of years. But also baleen falls out of the whale's mouth very quickly when the whale dies. So it's a time indicator. If we find the baleen, then we know that it hasn't, like the whale died and got buried pretty quickly. This whale died, and I think this whale died, and the baleen, I think, actually fell out of the mouth and landed on its flipper. Here's another whale, and you can see all the baleen in the mouth still. We call this the smiling whale. So to summarize what happened in the Pisco Formation, we have rapid deposition evident in sediments and in the fossils, and we don't have any long breaks in the deposition. So we can look at so in other words, somebody might say, oh, well, all the sediment was deposited rapidly, but still it took 13 million years because there were long breaks in the deposition. We don't find any of those breaks. We would see them if they were there, and we don't see them. And then there's very little bioturbation in the entire 640 meters, which is just really interesting. Again, it's an indicator that not very much time passed. So, and the reason I wanted to bring up the Pisco Formation is because this is relevant for the whole geologic record for the most part. So in the whole geologic record, we see this kind of pattern where we have rapid deposition, we have one layer on top of another on top of another. We don't have a lot of bioturbation, and we don't have long breaks in the deposition that are evident. And so for that reason, it's actually easier for me to fit the geology of the Earth into the biblical chronology than it is to fit it into a long evolutionary chronology. So in summary, remember that scientific data are pieces of a puzzle, and that in order to correctly interpret each piece, we need a guide. We need that puzzle box to show us, to give context to the piece to that puzzle piece. And our guide is the Bible, and nothing makes sense without it. I would say that in my research and in the research of several of my friends and colleagues, when we use the Bible as a guide, even though it's not a scientific textbook, it provides valuable information that helps us put together scientific models that explain a lot more data than other models can explain.